We are in Chapter 7, Calculus of Several Variables. Section 7.1 is Functions of Several Variables. We have dealt with cost, revenue, and profit functions with one variable. However, many companies produce more than one item in different prices. For example, a cost function with one product, X, is written as C of X, and the cost function with two products, X and Y, is going to be written as Cx, Y. Functions of two variables we'll say is z is equal to f of x, y. As a function of two variables, x and y are going to be independent variables, and z is going to be a dependent variable. The domain is the set of all ordered pairs x, y, such that f of x, y exists, and the range is going to be the set of all of those function values of x and y. You will see that if you were to graph these kind of functions, they are now three-dimensional because there's a z, an x, and a y, versus just an x and a y are two-dimensional graphs. So the first example that we have here says let f of x equal 2x squared minus 3y plus 7. Find the following. So if you notice, this is now a function not just in terms of x, it's now in terms of x and y. And so we know that x is equal to -1 and y is equal to 2. So in order to do this problem, we need to substitute in -1 for x and then 2 for y. Simplifying this and working this out, we end up with 2 times 1 minus 6 plus 7. 2 minus 6 plus 7 works out to being +3. The next one that we have is f of -4, so -4 is our x, and -5, and that's our y. So going ahead and substituting these in, we have 2 times -4 squared minus 3 times -5 plus 7. It's good to put your values that you're substituting in parentheses, that way you don't make any issues while you're evaluating this and using order of operations. So we have 2 times +16 plus +15 plus 7. So this works out to being 32 plus 15 plus 7, which works out to being 54. The next example that we have is the same function, however now we have f of h plus 1, and this right here is our x, and 2 is our y. So substituting this in, we have 2 parentheses, and then instead of x, we're going to put h plus 1 squared minus 3 times y, and y is 2, plus 7. So to simplify this, I need to multiply h plus 1 squared, which means h plus 1 times h plus 1, which if you were to go ahead and write that out and FOIL it and combine your like terms, you end up with h squared plus 2h plus 1, and then we have minus 6 plus 7. Then distributing our 2, we have 2h squared plus 4h plus 2 minus 6 plus 7, and then combining our like terms, we have 2h squared plus 4h, and then we have plus 2 minus 6 plus 7, which works out to being +3, and that would be our answer. The example right below this is a word problem, and it says a population that grows exponentially satisfies the function p of x, k, t. So this is going to be a function now not just of two variables but of three variables, is equal to a times e to the kt, where p is the population at time t, a is the initial population when t is 0, and k is the relative per capita growth rate. The population of a certain country is currently at 5 million people. It is growing at a rate of 3% per year. And it says, what will the population be in 7 years? So if you look at this, we do know that A is in our population, and that is at 5 million. We have our value of k, which it says that k is the relative per capita growth rate, which we know is 3% per year, so 0.03. And then we also know that t is equal to 7 years. We also know that since A is 5 million, I'm going to go ahead and just rewrite this as A is equal to 5. That way I don't have to keep worrying about zeros or rewriting the word million. I'm just going to say 5, and I'm going to let our population P is going to be measured in millions of people. So let P be measured in millions of people. And again, you don't have to do this. You can just leave it with 5,000,000. Definitely is another way to write your answer and still be okay. So we have our population, and it's going to be of A, which I'm going to call 5, K, which is 0.03, and T, which is 7, is equal to 5, e to the 0.03 times 7. And so we can simplify this and substitute this all in on our calculator, and we get 6.1684. And so we can say in 7 years the population will be 6.1684 million people. So in 7 years the population will be about, and it's 6.1684, and again it's in millions of people because that's how we chose to measure this. So 7.1 is more or less just kind of figuring out how to deal with functions now that are more than just one variable, and so hopefully we are okay with that. Then moving on, we get into the calculus part. So section 7.2 is partial derivatives. It says, remember dy dx gives the rate of change of y with respect to x. We will now extend this concept to include multivariable functions, functions in terms of 2 or more variables. So we have what's called a partial derivative of f with respect to x. There's a bunch of different ways to denote this. This is definitely something you want to star and make sure you know. So we have f, you'll notice a little x down at the bottom of x comma y, or dx or dz dx, and you'll notice that that's a d kind of cursive-y looking, and that's because that means it's a partial derivative instead of just a regular derivative, since it's more variables. So our partial with respect to x, or we can write it as z sub x, or we can write it as df dx, again with those weird d's to symbolize a partial derivative. So this is the derivative of f obtained by treating x as the variable, but that means that the other variables that you have in there aren't going to be treated as variables. They're going to be treated as constants. And then on the next page at the top, it says partial derivatives of f with respect to y, this time it's with respect to y, the other one is with respect to x, is going to be denoted f of y of xy, or the partial of z with respect to y, or z sub y, or the partial of f with respect to y. And this is, since it's in taking the derivative with respect to y, it's going to be the derivative of f obtained by treating y as the variable, and this time x is going to be as the constants. So the example right below this says, let f of xy equal 2x squared y cubed plus 6x to the 5th y to the 4th. Find, and it says f sub x of xy and f sub y of xy. So what this is asking for the first one is the partial with respect to x. So our partial derivative with respect to x. Now what that means, again, if you look back on the bottom of the previous page, means take the derivative of this with respect to x, treating y as a constant. So y is just like a number. So imagine it as just a number. So in order to do this, we have 2 x squared y cubed is our first term. And so taking the derivative of the first term with respect to x, we know that 2 and y cubed are both just constants. So you can treat those as just a constant and write both of those down. Times, we have to take the derivative of our variable. Remember, constant just stays there, we bring it right down. And the derivative of x squared would be 2x plus the derivative of our second term, the constant is just 6, and then y to the fourth times the derivative of x to the fifth with respect to x is going to be 5x to the fourth. And from here I would simplify this a little bit and clean it up. We would have 4xy cubed plus 30x to the fourth y to the fourth. And you can also rewrite this and factor out your greatest common factor, which would be, they both have a 2, they both have an x, and they both have a y to the third. So if we were to factor those out, your first term would be left over with a 2, and that's it. Plus, second term is a 15. You have 3 x's and a y left over, so x to the third y. And so these are both equivalent, and both are acceptable answers. So the next one that we have is going to be f sub y of xy, which is our derivative, partial derivative with respect to y. That means x is now our constant. So looking at that same function that we had up there that's typed, the 2x squared is just a constant. So I'm just going to bring that down, times y to the third, taking the derivative of this with respect to y is going to be 3y squared, plus second term, the 6 and the x to the fifth is just a constant. Taking the derivative with respect to y, it's going to be 4y to the third. Simplifying this again and cleaning it up, we're going to have 6x squared y squared plus 24x to the fifth y to the third. And again, we can factor out our greatest common factor. 6 goes into both of those. We have an x squared and a y squared. And then left over in the first term, we have nothing, so we would just write a 1. Plus, we have a 4. We have 3 x's left over, and we also have a y. And so again, those are equivalent answers. And so we took the partial derivative with respect to x, which was f sub x of xy, and the partial with respect of y, which is f sub y of xy. The next example says, let f of xy equal e to the 3x squared y. Find the partial f sub x of xy and the partial f of y of xy, so the partial with respect to x and the partial with respect to y of our function. So let's go ahead and start with our partial with respect to x. And again, this is a little bit different because we do have a chain rule that we have to use. And we have an inside function and an outside function. So if you remember, the derivative of e to any kind of function exponent is going to be rewritten exactly as it is, times the derivative of the exponent. So the derivative of the exponent with respect to x, that 3 and the y are just constants, and then the derivative of 2x, or of x squared, would be 2x. So this would simplify to 6xy e to the 3x squared y. And then taking the partial with respect to y. Again, we would have 3x squared y e to that power times the derivative of the exponent, but this time with respect to y. That 3x squared is just a constant times the derivative of y, which is just 1, if you would want to put that. So rewriting this a little bit cleaner, we have 3x squared e to the 3x squared y. The next example on the page, we're going to go ahead and circle, and we'll work on that one together in class. The top of the next page, This is second order partial derivatives. So again, we're going to take a second order partial derivative, which is just like a second derivative. And so taking a derivative of a derivative again. So it says let z equal f of xy be a differentiable function. We can then take a second derivative with respect to each of the variables. This would give us 4 second order partial derivatives. So you're able to take a derivative with respect to x and with respect to y. And then when you go to take your second derivative, you can do x twice, you can do y twice, or you can do x and y in different orders, and they're going to give you different things usually. So that is written there, all the 4 different ones that you would have. So the first one is d squared of z, and dx squared is going to be taking the derivative with respect to x of your function with respect to x again. So, and you can see written, it's also written as f of x, x, and likewise for the other 3. So the next example says find all second order partial derivatives. So for this, that means we have to find 4 things. So the first thing that we need to find is our first derivatives. So I'm going to go ahead and write f sub x of xy, and taking the derivative of our function with respect to x, we are going to have, it's negative 6x e to the 2y. So our terms that are going to be our constants are going to be negative 6 e to the 2y times the derivative of x, which is just 1. So I'm going to go ahead and just clean that up a little bit. Negative 6 e to the 2y. And then we also need to find the partial with respect to y of our function. And then taking the derivative of this, our constants that don't change is going to be negative 6 and x. And then taking the derivative of e to the 2y, we get e to the 2y, that stays the same, times the derivative of the exponent, which is just 2. And so cleaning this one up, we have negative 12x e to the 2y. So that is not what we are looking for. We're looking for all of our second order partial derivatives, but we do need these in order to find our second order. So let's go ahead and find our partial with respect to x twice. And so if you look at our partial, and I'll squiggly line underneath it with respect to x, you'll notice that there's no x's in it at this time. And so if you have a constant, which it is, it's negative 6 e to the 2y, which again, it's not the variable that we're concerned with, so that just is considered a constant. So taking the derivative of a constant is just going to be 0. So then we have our function that we had. We took the derivative of x first, so I write it first, closest to the f, and then with respect to y. So I have my function taking the derivative with respect to x, squiggly lined under, and I'm going to go ahead and write my constant down, which is negative 6 times, and then I have to write e to the 2y times the derivative of that exponent, which is just 2. So this simplifies to be negative 12 e to the 2y. So the next one that we have, I will double underline it, our derivative with respect to y is negative 12x e to the 2y. So let's go ahead and find our partial with respect to y twice. So putting 2 y's there of x comma y. And taking the derivative of this again with respect to y is going to be our constant, which is negative 12x. And then taking a derivative of e to the 2y with respect to y would be e to the 2y times 2, that derivative of that exponent. This simplifies to negative 24x e to the 2y. And then we also need to find our derivative with respect to x and to y, but this time the order that we have to go in is y first, and then x. And taking the derivative of y first, we've double underlined that. And now I have to take the derivative of it with respect to x. So I'm going to go ahead and write down my constant, which would be negative 12e to the 2y, since they do not contain an x, times the derivative of my variable, which is just x, which is 1. So this works out to be negative 12 e to the 2y. So those are my 4 answers that we have. So we have 4 second order partial derivatives for this problem, and they are all boxed. The next example that we have says find f of sub xx and f of sub yy, and it says of the function, and we have f of xy equals ln of the absolute value of 5x minus 7y. Why is there an absolute value on this function is because remember you can only take the log, any log, including the natural log, which we have here, of values that are positive, and that absolute value pretty much guarantees that we'll have a function inside that is positive. So in order to get my second derivatives, I have to first find my first derivatives. So I'm going to go ahead and find f sub x of xy in partial with respect to my function of x. And taking the derivative of ln of 5x minus 7y is going to be 1 over that function that we're taking the log of, which is 5x minus 7y, times the derivative of the inside function using that chain rule. And so taking the derivative of 5x minus 7y with respect to x, the derivative of 5x with respect to x is just 5. And then the derivative of 7y is just 0 because it has no x's in terms of it. So this simplifies to being 5 over 5x minus 7y. So from here, we are able to find f sub xx, which is going to be taking the derivative of this with respect to x again, and so you'll notice we have to use the quotient rule. So it's going to be the bottom times the derivative of the top, which is just derivative of 5 is 0, minus the top times the derivative of the bottom with respect to x, which is just 5, all over the denominator squared. So this is going to simplify. First thing's just 0, then we have negative 25 all over 5x minus 7y squared. In order to do our second one, we need to find our first derivative with respect to y. And so with respect to y, we have 1 over 5x minus 7y times the derivative of the inside, and this time it's the derivative with respect to y, which is just negative 7. So this is going to be negative 7 over 5x minus 7y. From here, I can find my second order partial derivative with respect to y twice. So we have f sub yy of xy. And again, we have to use our quotient rule. So it's going to be the denominator times the derivative of the numerator, which is just 0, minus the numerator times the derivative of the denominator with respect to y, all divided by our denominator squared. So the first term is going to be a 0 there. We have negative 7 times negative 7, which is positive 49, but times the negative would be negative 49, divided by, and our denominator is 5x minus 7y quantity squared. And so again, whenever you have those two sub values down there, those variables written, that tells you what to take our derivative of twice, or what the respect to. And you'll notice that the closest variable to our f, our function, is the one that you do first, and the farther one away is the one you do second. So the next example that we have says let f of xy equal 9x squared y squared minus 4y squared. Find our partial with respect to x, but this time instead of it saying xy, we actually have some values that we're going to substitute in. So in order to do this, I first need to find our partial of just xy with respect to x. So taking the derivative of our first term, the constant term that we have, constant part of it, is going to be 9y squared times 2x when I take the derivative of x. And then the second term that we have is minus 4y squared, which has no x's in it. So this simplifies to 18xy squared. From here, you can substitute in the values that we have, which is going to be when x is 2 and y is negative 1. So again, this is x and y. And substituting that into our problem, our derivative up above, we have 18 times 2 times negative 1 squared, which works out to being 36. The second example that we have on this page, we're going to go ahead and circle. And since we're dealing with anything, these equations that have to deal with two variables, now they're in terms of two variables, we're going to start dealing with equations of multivariables, which requires us to solve equations that have more than one variable in them. And we learned how to do this back in Algebra 1, and then reinforced again in Algebra 2, and so on. But we need to solve a system of equations. We had three different ways to do this. One was by graphing, which is usually not the best method to do. The second method was to use substitution. And then that third was elimination or the addition method. So go back and make sure you remember those three different methods. So the next part at the bottom of page 4 says the chain rule for partial derivatives. Suppose z is a function of x and y, each of which is a function of t. Then z can be regarded as the function of t, and we can rewrite this as d of z of t is equal to our partial of z with respect to x times the partial of x with respect to t. And we have the partial of z with respect to y and the partial of y with respect to t. The next example that we have says Adam manages a health store that carries two kinds of vitamin water, brand A and brand B. Sales figures indicate that if brand A is sold for X dollars per bottle and brand B is sold for Y dollars per bottle, the demand for brand A will be, and we have Q of X comma Y equals 300 minus 20x squared plus 30y bottles per month. She estimates that T months from now, the price of brand A will be X equals 2 plus 0.05 T dollars per bottle, and the price of brand B will be Y equals 2 plus 0.1 square root of T dollars per bottle. At what rate should Adam expect the demand for brand A to be changing with respect to time 4 months from now? Should he expect the demand to be increasing or decreasing at this time? So first of all, looking at this, you'll notice that you don't just have a couple variables, you actually have quite a few. You have X and Y, we have Q, and we have T. So I need to find the demand for brand A to be changing with respect to time 4 months from now. And it says, should we expect the demand to be increasing or decreasing? So I need to find our derivative of our function Q with respect to time. And this is going to be when our time is equal to, it says, 4 months from now. So we'll say for 4 months. So in order to find this, I'm going to take dq dt, and I can look at this and say I'm going to find the partial of q with respect to x times the partial of x with respect to t. You can almost think of it as though those dx's, so those partials with respect to x, cancels out, and we have dq dt. And so from here, I also need to take this not just for one brand, but for the second brand. So adding together our partial of q, but this time with respect to y, times our partial of y with respect to t. And again, this is allowing us to take those partial derivatives, and it was written right up above, with respect with multiple functions, and doing a chain rule in regards to that. So from here, we know that taking the partial derivative of q with respect to x is going to be, if you look at your q function up here, taking that with respect to x, we have negative, it's going to be negative 40x times taking the derivative of x, and with respect to t, which is going to be 0.05, plus taking again the derivative of our partial derivative of q with respect to y this time is going to be 30 times the partial of y, which we have down here with respect to t. And for this one, I'm going to go ahead and rewrite our function over here as y equals 2 plus 0.1 t to the 1/2. And so we have 0.1 times 1/2 t to the negative 1/2 power. And you can clean this up if you want. You can leave it like this also, because we still have to evaluate this when t is equal to 4. So I need to evaluate this when t is equal to 4. However, you'll notice that we don't just have t's. I don't have just t's, which is right here. I also have an x. So from here, I need to figure out what x is when t is 4. So how do you find x when t is 4? If you look at your formula up above, x is equal to 2 plus 0.05 t, and instead of t I'm going to write 4. When you work this out, you get 2.2. So I'm going to substitute in for x 2.2 and substitute in 4 for t. So we have negative 40 times x, x is 2.2, times 0.05 plus we have 30 times 0.1 times 1/2 times t, and t in this problem is 4 to the negative 1/2 power. So going ahead and substituting all of this in on my calculator and getting an answer, let's go ahead and round 2 decimal places. And when we do, we get negative 3.65. And it says up above, should we expect the demand to be increasing or decreasing at this time? So what this means is, so in 4 months from now, the monthly demand for brand A will be decreasing because it's negative at a rate of 3.65 bottles per month. So the next section that we have is 7.3, which is optimizing functions in 2 variables. And this is in chapter 3, we learned how to find maximums and minimum points with calculus. This is an extremely important application, especially in business. We will now extend this idea to find the extrema of a function in 2 variables. Informally, we can think of relative extrema as high points and low points on a surface of z equals f of x comma y. So we're not getting into the graphing aspect of this, but you can see that in those pictures where you would have those relative maximums and those relative minimums. And then you'll notice too that we also have something called a saddle point, and we will take a look at that in just a minute. But it says a function down here has a relative minimum at a point AB if f of AB is less than or equal to f of xy in some region containing that point. And likewise for a relative maximum, the same thing, but it would be greater than all those other values. The location of the extrema, let's give that a star, says let z equal f of xy have a relative maximum or relative minimum at the point AB. Says let f sub x of AB and f sub y of AB, so the partial with respect to x and the partial with respect to y, both exist at that point AB. Then our partial derivative with respect to x and our partial derivative with respect to y at that point would also equal 0. The next definition that we have is called a saddle point. There is a picture of a saddle point on the right, and it says has a minimum while approaching from one direction, but a maximum while approaching from a different direction. It is neither a minimum or a maximum. It is called a saddle point. So you'll notice that in the directions for the problems, they'll ask you to find extrema or saddle points. And to find our critical points, these are the points A, B, such that our partial derivatives with respect to x and our partial derivatives with respect to y at the point A, B are going to equal 0. So the first example that we have on here says to find all critical points for our function fxy, which is equal to 4x cubed plus 3xy plus 4y squared. And in order to do this, we need to take our partial derivatives. And so our partial with respect to x of xy, taking the derivative of this with respect to x, zoom in here, and we are going to end up with 12x squared plus taking the derivative of 3xy, the 3 and the y are the constant, taking the derivative of the x, it would be 1. And then the derivative of 4y to the third is just going to be 0 since there is no x variable in it. And then taking the partial with respect to y of our function, the first term that we have, 4x cubed, has no y's in it, so we don't have to stress about that. That would be 0. And then the derivative of 3xy with respect to y is going to be just 3x. Plus, and then we have 12y squared. We are going to set both of these equal to 0. And then to solve this, I'm going to go ahead and I will solve my first equation for y. And so I have 3y is equal to negative 12x squared. And then dividing both sides by 3, we have y is equal to negative 4x squared. I am then going to substitute this in for y in my other equation down here. And when I do, I have 3x plus, and then 12 times y, and instead of y, I'm going to write negative 4x squared to the second power equals 0. And now from here I need to solve this. So I have a 3x plus 12 times, and then this is going to be negative 4 squared is 16. X squared squared will be x to the fourth is equal to 0. And then I have 3x plus 12 times 16 is 192. X to the fourth is equal to 0. Factoring out my greatest common factor, which is 3x, I have 3x 1 plus 64 x to the third equals 0. Using our zero product property and separating these and setting each of these equal to 0. I get x is equal to 0, and I get x is equal to, and we'll go step by step, x cubed would be equal to negative 1 over 64. Taking the cube root of this, the cube root of negative 1 is negative 1, and the cube root of 64 would be 4. So we get x is equal to negative 1/4. And so we have two values of x here. And so in order to find my, what they're called as critical points, I need to not just find x, I now also need to find our y value. And the easiest one to substitute this into is where we had y equals negative 4x squared. And so if I were to substitute in 0, we have 0 squared, which equals 0. So we have 1 point at 0, 0. So this is one of our critical points. And then I need to substitute in negative 1/4. So I would have y equals negative 4 times negative 1/4 squared. This works out to be negative 4 times 1 over 16. And this works out to be negative 4 over 16, which reduces to negative 1/4. And so we have a second critical point. Our x value that we substituted in was negative 1/4. The y value that we got out was also negative 1/4. And so these are both my critical points. And that's where those partial derivatives are equal to 0. The next thing that we have is called the test for relative extrema. For a function z equals fxy, let the second partial derivative with respect to x twice, with respect to y twice, and fxy, so with respect to x first and then with y, all exist in a circular region containing the xy plane with the center AB. Further, let f sub x of AB equals 0 and f sub y of AB equals 0. So the partials with respect to x and the partial with respect to y at that given point is equal to 0. And it says with a discriminant, so this is our new word here, and we call this capital D. The discriminant is going to be defined as the second partial derivative with respect to x twice times partial with respect to y twice minus the partial with respect to x, then y squared. And once we work this out, we'll get a value for d. And since we're valuing it at point A, B, and it says then our point is going to be a relative maximum if our discriminant is greater than 0 and our second order partial derivative with respect to x twice is less than 0. And then we have a relative minimum if our discriminant is greater than 0, but our second order partial derivative with respect to x twice is greater than 0. And then we have a saddle point if our discriminant is less than 0, and if d equals 0, the test gives no information, and we'd have to go about it in a different way. We don't really see that in our class. So this is definitely something that we need to know. And this is going to be the same as what we have on the next page. So this is just the same thing. It's just listed as a table instead of as a list of information. So summarizing it, your discriminant can either be greater than 0, equal to 0, or less than 0, and it tells you what happens from that. So the next example that we have says to find all points where the function have any relative extrema and to identify any saddle points. So those are the directions that you typically will see when doing these problems. And so first thing is I need to find my second order partial derivatives. And in order to do that, I need to find my first order partial derivative. So f sub x of xy is going to be taking the derivative of my function with respect to x. The first term would be 3y. 6y is going to be 0, and then minus 5. And then taking the derivative with respect to y, my partial derivative. The first term is going to become 3x plus 6y, the derivative is just 6, and then 5x would be 0. So in order to find our critical point, that point AB, we need to solve this. And you'll notice that setting each of these equal to 0, you will find that y is equal to adding 5 and dividing by 3, 5/3. And x is equal to subtracting 6 and dividing by 3 to -2. So from this, we get our value of a and b is -2, 5/3. And again, this is our critical point, and written in the formulas up above it is our a, b. So the next thing I need to find is my second order partial derivatives. So I need to find f sub x. And if you look at your first derivative with respect to x, we have 3y minus 5. There's no x's involved in that, so the derivative of that would just be 0. And then we need to find our second order partial derivative with respect to y twice. And if you look at your first order derivative of our function with respect to y, we have 3x plus 6, which has no y variables in it, so again the derivative of that would just be 0. And then I also need to find the derivative with respect to x first, so looking up here at the first order partial derivative with respect to x. Then I need to take the derivative of that with respect to y of xy is equal to, and the derivative of 3y minus 5 with respect to y is going to be 3. So from this, I am able to figure out d, which again is my discriminant, which is going to be copying down the formula that we had up above, and then squaring our partial with respect to x, then a y, And you'll notice that we're evaluating these at a, b, and that a, b up here is our critical value. So if you want to put down, this is our point a comma b. So substituting in now a and b, which is -2, 5/3 for both of these, and then -2, 5/3 again, and then subtracting our partial with respect to x, then with y of -2 5/3, and then squaring that. This problem is a little bit nicer because when you evaluate the first term that we have up here, you'll notice that you just get 0 times, same with y, when you substitute in that point you would just have 0, minus, and then substituting in fxy at -2, 5/3, you just get 3. So minus 3 squared. And this is going to work out to being -9. And this is our d value, our discriminant. And since this is less than 0, we know that it's negative. And you can either look up here or up even higher. And you can see that if your discriminant is less than 0, you have a saddle point. So we'll put down that we have a saddle point. So since d is less than 0, the point -2, 5/3 is a saddle point. So we have another one of these right below. Same approach, same directions. So first thing that we need to do, I'm going to zoom in, is find our derivative with respect to x of x comma y. And taking our derivative with respect to x, we're going to have 2x plus y minus 6. Again, y squared and -3 would be 0 since they do not have a x value in them. And then taking our partial with respect to y of x comma y, we end up with x plus 2y, and then the derivative of 6x and 3 would be 0. Setting these both equal to 0, you'll notice that I have two equations with two unknowns, and this is going to require me to do a little bit more work and solve this as a system. So I'm going to go ahead and solve my second equation for x, and this is equal to -2y. I am then going to substitute this in for the x in the other equation, and when I do, we have 2, and then instead of x, I'm going to put -2y plus y, and then minus 6 is equal to 0. This I can solve, so I have -4y plus y minus 6 is equal to 0. And then keep simplifying this. We have -3y minus 6 equals 0. Adding 6 and dividing by -3, we have y is equal to -2. From here we can find our x value by substituting it in. Easiest one to substitute it in is where we solved for x in the first place. And so we know that x is equal to -2y, and x is equal to -2 times -2. So our x value would be equal to +4. And so the point that we have for AB is going to be 4, -2. So that's the value that we are checking to see if we have a relative extrema or we have a saddle point there. So in order to do this, I need to find also second order derivatives with respect to x twice. So we found it with respect to x once, and we have 2x plus y minus 6. And taking the derivative of this with respect to x again, we just get 2. Taking our partial of y with respect to y again, we have x plus 2y. Taking the derivative with respect to y again, we get just +2. And then taking our derivative with respect to x, which we did up above, and now with respect to y, so taking the derivative of 2x plus y minus 6 with respect to y is going to be just +1. So now from our formula, we have our discriminant is going to equal the second order partial derivative evaluated at our point, which is 4, -2, times our second order partial derivative with respect to y twice of 4, -2, minus the second order partial derivative with respect to x, and then to y at 4, -2. and then squared. So from here, we know that our second order partial derivative with respect to x twice is 2 times second order partial derivative with respect to y twice is 2 minus our partial with respect to x then to y is 1, and then squaring that. So this works out to being 4 minus 1, which is 3, which is greater than 0. So looking up above at my table or at the way that it was written out before, if our discriminant is greater than 0, we have two options that might happen. It could be a relative maximum or a relative minimum, and so I have to look at my second order partial derivative with respect to x twice to determine if it is greater than 0 or less than 0. So for this problem, I know that d is greater than 0, so our discriminant is greater than 0, and our second order partial derivative evaluated at the point 4, negative 2, if you look at that, is 2. And this is greater than 0 also. And since that this is greater than 0, we know that we have a relative minimum. So we have a relative minimum at 4, negative 2. So the example on the next page, we're going to go ahead and circle and work on part C together in class. And then we're in section 7.5, which is constraint optimization, the method of Lagrange multipliers. In many applied problems, a function of two variables is to be optimized subject to a restraint or a restriction or a constraint on the variables. And so we have a production function, which is z equals f of x, y, is a function that gives the quantity z of an item produced as a function of x and y, where x is the amount of labor and y is the amount of capital, in appropriate units. So make sure you underline the units and understand what the units need to be expressed as. Needed to produce z units. If the production function has the form z equals f of x, y is equal to, and this is a, capital A, times x to the lowercase a, and y to the 1 minus a, where a is a constraint, and lowercase a is between 0 and 1, and including 1 and not including 0. This is called the Cobb-Douglas production function. The example right below says a manufacturer of mountain bikes estimates that his total production in thousands of units, which we'll underline so we know our units, is given by f of x, y equals 3 x to the 1/3, y to the 2/3, where x is the number of units of labor and y is the number of units of capital utilized. Part A says to find and interpret the partial derivative with respect to x at 64, 125 and the partial with respect to y of 64, 125 if the current level of production uses 64 units of labor and 125 units of capital. So first thing that we need to do is find our partial with respect to x. So we'll go ahead and do that. And taking our partial with respect to x, we are going to have 3 times, and then we have 1/3 x to the negative 2/3, and then our y is just a constant. We can clean this up a little bit and write this as x to the negative 2/3, y to the 2/3. And so our function at 64, 125, substituting in those values into our partial derivative with respect to x, we have 64 to the negative 2/3 and 125 to the 2/3. And working this out, we get a value of 1.5625. And what this symbolizes, this is our approximate, as we did round, change in production, which is what our Z is, or our f of x, y, and we measure our production levels in thousands of units. So our productions, and we'll say in thousands of units. And when we took our derivative, we took it with respect to x. And if you remember, x is the number of units of labor. So this would be for 1 unit change in labor, which again is our x variable that we'll write down. So we need to do the same thing, but this time we need to take that partial with respect to y. And so taking our partial with respect to y, it is going to be 3, and the x to the 1/3 would stay the same, times taking the derivative of y to the 2/3. You have 2/3 y to the negative 1/3. Cleaning this up, we have 2x to the 1/3 y to the negative 1/3. And then we need to evaluate this again at 64, 125. So f sub y of 64, 125, and substituting in those values for x and y. X again is 64, y is 125. When we work this out, we get 1.6. And so explaining what this represents, this is the approximate change in production because we're taking the derivative of our function z, which is in production. And again, this is measured in thousands of units. For 1 unit change. And the variable we took our derivative of with respect to is y, which represents our capital. So this would be the approximate change in production in thousands of units for 1 unit change in capital. And I'll put down in parentheses y, since that was what we were taking our derivative with respect to. The problem continues on to the next page, and part B says, use your answer from part A to calculate the approximate effects on production of increasing labor to 65 units while holding capital at its current level. So we had our partial, if you notice 65 is changing, so increasing labor. So that was our partial with respect to x, and at 64, 125 from part A, looking up above, we got 1.5625 from part A. And so since we're dealing with in thousands of units, this would be the same thing as 1,500, and we'll just round it and say 63. That way it's a nicer number to deal with. And so this is, again, from part A, this is approximate change in production in thousands of units, and we rewrote it for 1 unit change in labor. And since we changed it from 64, which is what we had originally, to 65, we increased it by 1 unit. Our labor increased by 1 unit. And so this is going to be an increase of approximately and so we increased by 1,563, and what we're talking about is, if you go back up and look, was mountain bikes. So I'll just put down bikes. So if we are able to increase our labor from 64 units, however they're measuring that, to 65, we can increase our production of mountain bikes by about 1,563 bikes. So the next example that we have says the production function z for the US was once estimated to be z equals 0.7 y to the 0.3, where x stands for the amount of labor and y is for the amount of capital. Find the marginal production of labor and of capital. And so since x is our labor, we are going to have x is equal to labor. We need to find our function, the partial derivative with respect to x of xy. And since y is our capital, we need to find our partial with respect to y of x comma y. And so this is going to give you your marginal productivity of labor and your marginal productivity of capital. So I'm going to go ahead and circle this one, and we'll finish it together in class, but see if you can take those partial derivatives of our function, of our productivity function, on your own. Next up is section 7.6, which is double integrals. So integration was first introduced in chapter 5 and 6. We will now extend upon this idea to integrate functions of two variables. To do this, we will need to integrate our function that is going to be in respect to x and y with respect to one variable while holding the other variable constant. So our first integral that we have listed here says evaluate the double integral, and I had the integral from 0 to 1 and then the integral from 1 to 2 of x squared y dx dy. And so I'm going to go ahead and rewrite this, and I'm going to put that part, we're going to start with the inside, and so the part on the inside I'll put in parentheses, leave a little bit of a space there in front of it. So we're going to integrate x squared y dx, and outside of the parentheses I'm going to put my integral from 0 to 1, and that's with respect to y. And so I need to integrate this part first. So we start on the inside and work your way out. So integrating this with respect to x, and the reason why we're doing this with respect to x is because it's a dx. That means we're treating y as a constant and x is my variable. So integrating this, you would add 1 to your exponent and divide by that same number. And since y is just a constant, it just stays there. And then we need to evaluate this, and this is from x equals 1 to 2. And I'm going to go ahead and bring down the rest of the integral that we have with respect to y, and we'll deal with that after I finish simplifying my part inside the parentheses. And so from here, I'm going to substitute in 2, so I have 2 cubed over 3 times y minus my lower limit of integration, which is 1 to the third over 3 times y. Again, bringing down my integral symbol and my dy. This is now going to simplify to 8 over 3y minus 1 over 3y, so it simplifies to 7/3 y. So we have the integral from 0 to 1 of 7/3 y, and again dy. And so now we're going to integrate again, this time with respect to y. And so we have 7 over 3 is just a constant, times adding 1 to the exponent and dividing by that same value. And again, since it's a definite integral, we're going to evaluate this from y equals 0 to 1. And so 7/3 times the 1/2 is going to become 7 over 6 y squared, evaluated from 0 to 1. So we have 7/6 times 1 squared minus 0 squared, which works out to be just 7/6. And this is our answer for our double integral. So on the next page, we have 2 other examples, and we're going to go ahead and circle both of those, and we'll work on those both together in class.